Hi, I'm Tim Berglund with StarTree. Welcome to Apache Pinot 101, Architecture, Tables, and Segments. To begin our journey into Pinot in earnest, let's start with the core abstraction that you're going to see and think about and deal with the most, and that's a table. Tables are where data is stored in Pinot. And at a top level, there's no magic here. You don't need to trick yourself into thinking about anything different. It's just a table. It's got rows and it's got columns, and the columns have names and data types, and you have lots and lots of rows. That's what a table is. Tables are designed, as we get into the details, to grow very, very large. So in terms of width, number of columns, that's going to be sort of normal. You'll have maybe dozens for a big and complex table. But in terms of rows, well, that just gets as big as you want it. So tables are able to scale to arbitrarily large row sizes. So rather than use a complex, hacked together, extended create table SQL statement or proper DDL, what we do with Pinot is we just have two JSON files. Ends up being a lot easier, a lot more clear. We have one that defines the table schema and the other famous table config file. And that really is the central point of a lot of your configuration activity in Pinot. Tends to revolve around table config. It talks about lots of different things. We'll see those as we move through the course. But one that we'll cover here is what type of table it is. Now, fundamentally, there are two types of tables in Pinot, real-time and offline. So the trick about an offline table is it's completely available, live, probably being replicated in the cluster, available for queries. You could be ingesting new data into it. It's completely alive. Calling it offline doesn't mean that it's somehow on standby mode. That just means that it contains batch data, and there is no streaming ingest going into that table. A real-time table, by contrast, is being filled up with data that's coming from some streaming source. That's usually Kafka. So a real-time table you can think of as just having a Kafka topic bolted onto it, and messages are being consumed, filling up that table all the time, constantly. As long as messages are produced to that topic, they'll be ingested into the table. Now, a hybrid table is like a combination of the two, and this is pretty understandable because maybe you've got, say, some giant collection of Parquet files in S3 or Avro files or JSON or something that's historical data sitting off there in some kind of static batch sump, and you'd like to ingest that and have that be your historical data. But with the same schema, you've got messages coming in from a Kafka topic that are things happening right away. You might kind of have an offline and a real-time component. Well, that's a hybrid table. So, and under the covers, it's really like, in Pinot, if you look at how it's built, it's like there's an offline table and a separate real-time table. But from the developer point of view, what you're going to see in querying that table, dealing with that table, you just see the one thing. Now, between the schema and the table config, when you're describing the columns in the table, it's noteworthy that every column, because this is an analytics database, is either a metric or a dimension. And there's a special kind of dimension called a date time. And every table needs at least one date time column. So fundamentally, everything is either something you're trying to measure that'll probably show up in an aggregation somewhere at some point, or some dimension by which you might filter or group that metric. So every column, either a metric, a dimension, or a date time. Now, when we start to think about implementation, how this thing is actually made, how it's put together under the covers, tables are stored in units called segments. So a segment is something like a shard or a partition in a traditional database, but the segmenting process is kind of invisible to you. You define the table, you create it, you set up the ingest, whether that's offline ingest or real-time streaming ingest, and segments are happening. They're a very important part of the way Pinot is constituted, but you don't see that. You just see one table. You get to issue queries against that table, and you don't really have to think about what segment they're in when you're doing those queries, which is fantastic. If you've got an offline table, segments are created sort of outside of Pinot, or at least outside of where they're stored, and then they're pushed into the cluster. Now, there are some built-in command line utilities that you can use to do that. So like I said a minute ago, if you have this giant collection of JSON files in S3 or something like that, there are command line tools that you can run to do that ingest, to populate an offline table with that data, to create those segments. In terms of the internal implementation, they're being created outside of the cluster, pushed into the cluster, and then assimilated as a part of the data that defines that table. For a real-time table, again, you define in the table config a connection to Kafka, and those segments, the data in that table segments, are constantly being consumed from the topic that the table is connected to, all the time by that consumption that Pinot is doing. There are those standard included command line utilities for ingesting data in a few standard file formats. And if you want to do this yourself, and this is not particularly unusual, if you've got, say, a Spark cluster or a Flink cluster or even Hadoop, there are APIs for all those systems for you to be able to create segments from, and this is again for the offline case, if you've got batch data lying around, say in Spark, you can create segments with that Spark API, push them into the cluster, populate your offline table. You can also do that with Flink, a stream processing system. If you have a stream that you want to process and use that to create offline segments to push into an offline table, you can do that as well. Now, if you need a picture, logically speaking here, this is not in terms of any physical implementation, but I just want to emphasize, we've got a table, and a table is composed of segments. We have these segments, and they are showing just a few here. There could be lots and lots of segments that compose this table. Each segment is a collection of a certain number of rows in the table. So you can imagine just a big giant table, dividing it off sort of in vertical chunks, and each one of those vertical chunks becomes a segment that composes the table. It's worth thinking a little bit about how segments themselves are put together. Now, very key point here. Pinot is an analytics database and optimized from the ground up to be the fastest analytics database that it can possibly be. That means that it is going to be a columnar database. Data is going to be stored in columnar format. So rather than, imagine a row, because again, you're a normal person. You're thinking about a table. You're thinking about your data in terms of rows. You look at that row and you say, okay, here are all the bytes that compose this first field, and we'll take the second field and serialize it as bytes. If you just serialized all those fields as bytes and strung them together, you might think, let's persist that. Let's write that to disk like that row. And that seems like an intuitive way to do this if you haven't thought about this before. That's great if you're a transactional database and you're normally concerned with that one thing, that whole row together. But this is an analytics database, so we are more likely to want to scan over multiple values of a single field so that we can aggregate them, right? We want to filter so that we get some view of this number of rows of just this one metric. We want to see those and read those efficiently. Well, to do that, we have to store those column values contiguously. And I'll show you a picture of that. It's the first time you thought about this in a minute. I'll give you an illustration in a minute. A few other key points. Dimension columns, that is things that are likely to appear in the where clause and not the things that we're aggregating in the projection or the aggregate part of the query. Those are often stored dictionary encoded. It's typically the case that dimension columns don't all have a unique value. There's probably some smaller subset of unique values, small relative to the number of rows in a segment. And so those are stored with dictionary encoding. Typically. Don't have to be, but they often are. And there are plenty of advantages in terms of storage footprint and performance to be had from that. The indexes, we haven't talked about indexes yet. We have a whole section on indexes in this course. Indexes are stored with the segment. So a segment is all of the rows, it's some subset of rows in the table, stored as chunks of columns, plus whatever indexes we've defined on those columns, all stored together. Key point, once written, a segment is immutable. We never go back and change the values in a segment. Once it's written, it's been written. Now, we are willing to forget about a segment after a certain amount of time, right? That seems to make sense. We can configure a retention period. Maybe we only want to keep this data around for a month or 6 months or a week or something like that. That's all something you can say in the table config. And once a segment becomes older than that retention period, we can let it die. Now, for some of you, me saying segments are immutable and once data is written, it's there forever until it expires and it's too late, you can't change it, that might worry you. Well, we've got a module on what Pinot calls upserts. That's a really, really important thing that Pinot does well as a real-time analytics database. And we can explain how, even though segments are immutable, you can, in some cases, make updates to values that you've already written. Now, let me just quickly walk you through visually what I mean by Pinot being a column or a column-oriented database. So this is somewhat conceptual, but it really gets the right point across. Now, imagine that's our data. That's like looks like some clickstream data. Those are the records that we've been ingesting, JSON records that we're using to create a segment. What we're going to do is we're going to take, a million of those, 200,000 of those, I don't know, some number of rows, and gather all those up and make a segment. So we're going to first take all of the values of the IP column and store those all together. All of the values of the user ID column, store those together. I don't know that those would dictionary encode too well necessarily, so maybe those take up a lot of space. Remote user, same thing. Maybe there are a lot of unique things. Time, that's a date time column. That's a metric, so that's going to take up some space. And request, well, an HTTP request, that's gonna dictionary encode like crazy, right? So that might take up less space on disk. Same thing with status. Hopefully we don't have too many of those, right? There are only so many defined. Bytes, that's another metric, but you see what's going on here. All these are stored contiguously on disk, all of the column values. So zooming in on IP there, what that really is many, many, many little, individual values of the IP addresses that we've seen in these requests. That's what it means to be a columnar database. And that's not super obvious here, but say if you were looking at bytes, those are less interesting numbers to look at, but you wanted an average of the bytes based on a certain range of times, and you had things sorted by that by time, then you could just scan through those columns and efficiently read all those things in and compute your aggregation. So that's why Pinot is columnar and really what it means to be a columnar database. So that is tables and segments, some real Pinot fundamentals. If you've got that down, you can move on.